Hello students, in this video we'll discuss the principle of mathematical induction and see applications when it can be used to prove relatively elementary mathematical statements. So, the principle of mathematical induction states that if you have a indexed family of statements, if P of n for n bigger than or equal to 1 is an indexed family, of statements for which two things are true, for which one, we need P of 1 to be true, so the first statement is true. And the second condition is that if pk is true, so if pk is true for k less than or equal to n, then Pn plus 1, the next statement in the series, is true. Then Pn is true for all n bigger than or equal to 1. So this is the statement of mathematical induction. And this is one of the axioms of mathematics. So this is something that we need to assume this principle of induction is true in order to prove things. So let's see an example of this. So let's prove using mathematical induction. Prove using induction that 1 plus 3 plus 5 plus 2n minus 1, so this, we can figure out what this is in a second, is equal to n squared. So we have over here, and we want to show that this is true as induction for all n. Now what we have over here is we have 1 plus 3 plus 5 plus all the way up to 2n minus 1. This is the sum. This is the sum of the first n odd numbers. So let's use induction. So to prove this, proof, we will let Pn be the statement one plus 3 plus 2n minus 1 is equal to n squared. And so now we have to verify that 1 and 2 are true. So let's look at statement number 1. So if I look at n equals 1, the question becomes, is it true when n is equal to 1, 2 times 1 minus 1 is just 1, so there's only one term in the series. Is 1 equal to 1 squared? Well, that is true. So we verified that statement 1 is true. Now we're going to assume that 1 plus 3 plus 2n minus 1 is equal to n squared. We will assume that, and we want to show that the same thing is true for n plus 1. So then we'll consider 1 plus 3 plus 2n minus 1, and then we'll add one more odd term. So one more odd term will be 2n plus 1. And so now we see by the induction hypothesis, we know what that first set of n terms are going to be. That's going to be n squared by our assumption. So here's where I'm using this assumption. And then I have to add on to that this 2n plus 1. But now we see that this is n squared plus 2n plus 1, which is exactly n plus 1 quantity squared. So we've shown that the next statement, Pn plus 1, is true. So Pn plus 1 is true. Therefore, this expression, 1 plus 3 plus 5 plus 2n minus 1 is n squared is true for all n by induction. So now we apply mathematical induction to complete the proof. There's an alternate way of proving this geometrically, which is sort of neat, so we can mention it. If I draw one dot over here, that would be 1. And if I draw 3 dots around it to form a square. That will be a 1 over here, then a 3 over here. And so we know that 1 plus 3 is equal to 4, but I have a 2 by 2 square. If I draw 5 dots, 1, 2, 3, 4, 5, I've now formed a 3 by 3 square, so 1 plus 3 plus 5 is 9. And I can add 4 dots on top and 3 below it, and that adds in 7, and that gives me a 4 by 4 square. So we can actually prove this statement over here, not by induction, but proving by this geometric configuration. 1, 2, 3, 4, 5, 1, 2, 3, 4. Now I have 1 plus 3 plus 5 plus 7 plus 9, and that gives me a 5 by 5 square, or 25. So we can geometrically visualize how to prove this, or we can prove it with mathematical induction. Thank you very much.